Hi, my name is Ben Mears, and in this video, I'll be presenting my COMP431 Extra Credit project. In this project, I chose 3 websites to run experiments on: Seattle University, Twitter.com, and Cambridge University in the UK. I first ran a trace route on each of these websites to understand the path of routers that my packet of information takes to get to those websites. The trace router for Cambridge is 20 routers long, the trace route to Twitter is 10 routers long, with 1 request timed-out error, and the trace route for Seattle University is 12 routers long with 18 request timeout errors. Then I conducted a series of ping experiments in different timeframes of a weekday, which was on Tuesday, April 28th. In each of these experiments, I used the ping command in the terminal to test the average loss and delay of a packet's round trip time. Every time I did this, I did it 60 times in 1 minute. I did this for each router in each experiment 5 different times in that one day. These timeframes were early morning, mid-morning, mid-afternoon, evening, and night. In this video, I'll be presenting my process of gathering my data and the findings that I have gathered. In the description of this video, I have provided links to the GitHub repository and the Google Sheets and the Google slide presentation that I'm currently going through. So all of the methodology is there. You can see the functions that I wrote, and you can see the data itself either in the GitHub repository or in the Google Sheets, whichever you prefer. Okay, so first I'd like to take you through my process. So we look at the process here. We see that, so the first thing I did was go to Twitter, or do a trace route of each website. So if this is twitter.com, this is the example. So we see that the trace route went reasonably well. There was 1 request timed out, but I ran each trace route several times to see if I could figure out what that was, but it would be timed out every time. And we have the IP addresses here, which are notable. So then what I did is I made this Python file where I put each of those IP addresses for each route in an array in order. And then I made a run ping experiment function, which takes in an array and an output file and goes through each IP address in the array and runs a ping trial, and then outputs it, and outputs it to a parse ping function, which then outputs it to a file so that I can use the data. So here's the parse ping function. And so every time, all I had to do in the process, instead of sitting here all the time and typing in the ping trial over and over again, I just had to change the output files and then click run and make sure my computer didn't go to sleep. And then the next and last thing, so I guess I'll just show you here's my example output file from one of the ping trials. This is the afternoon Twitter, so you can see the ping, the average, and the loss percent. So it's not beautifully formatted, but it's good enough. And so then we see the extra credit, the Google Sheets here, which has all of the data. So you can see all of the data here. It's a lot. I've shared this in the link, so if you'd like to take a closer look, you can. All right, and now here is, you can tell this isn't the first time I've done this. Here's the presentation. So this is my presentation for COMP431 Extra Credit. My name is Ben Mears. Okay, so the first experiment that I did was with Seattle University. And so generally speaking, I did 4 types of graphs in each experiment. So for each experiment. So the first type of graph is a one with router addresses in order of the traversal. So this is in order of hops basically, and average delay in milliseconds is the Y. So we can see that with each hop, we can tend to expect, with this linear pattern here, we can tend to expect that with each hop, each hop, you can expect a higher delay. That is something that can be reasonably expected based on this. So the next type of graph that I did was average loss per router to Seattle. So we have these router addresses here. This is in order of the traversal, and this is the average loss percent. So what I did here is take each of the 5 trials and look at the router and look at the average loss percent when you take the 5 trials, add them together, and divide by 5 basically for each router basically. So I was trying to figure that out, see if there was any kind of pattern, and we don't see any clear discernible pattern here. Maybe slightly larger loss percent with more hops. As you can see, like this is higher than this, like the first three are lower than all of the last 3. That's possible, but it's definitely not a strong correlation. Not at all like this is a very strong correlation. By the way, this is using the same methodology where you take the router in each of the 5 trials, add them together, and divide by 5. Okay, so then we take the third type of thing that we do is an average delay versus time frame. So we take the average delay of every router and then divide it by the total, and then add them together in the time frame, of course. and then divide by the amount of routers, and then we get the average router delay per time frame, basically, per router per time frame. So we see that the router delay is definitely the highest in the early morning at 80-ish. And then we see mid-morning and mid-afternoon, it's tied about for the lower one, and then these evening and night are later. So the important thing is that morning is the highest, and mid-morning and mid-afternoon are the lowest average delay per time frame. Okay, and then we look at the average loss per time frame. This is a very interesting graph. Again, this is the same. This is the fourth type of graph that I'll be doing. It's the same methodology as the one before, where we just take the average loss percents, which are the y-axis, and the time frames with the x-axis, as you can see, and we add them together and then divide by the number of routers. There actually wasn't any losses in the early morning, which is pretty cool. But we see that there's definitely an outlier here. So we've got the 4 early morning, mid-morning, mid-afternoon, evening, which are lower than 0.25%, and the night skyrockets to 0.82%. That's significant, but I do think that this is a bit of an outlier. You'll see why in future, with future data presented. The most important thing to note is that this wasn't just like a one router issue. This was 3 different routers had a 3% loss rate. So that is, it's not just like one router had a mistake. So it's hard to consider an outlier, but it's definitely a weird data point. So now we look at the anomalies. So the destination was an AWS server in Portland, Oregon. All subsequent requests in the trace timeouts, even when the maximum number of hops is increased to over 100. So I tried, but it just, all of them timeout. The last router to work in the trace was also an Amazon server. I don't know how significant that is, but I did think it was notable that the destination and the last one were Amazon and nothing worked in the middle. One router had request timeout ping errors in the mid-afternoon and evening tests. Mid-afternoon and evening is the important thing to remember there. And these were left out as instructed. The 12 hop registered an error during every time frame, so it was left out of the results entirely. And the cause of the errors, any errors here, is likely increased congestion, which causes the router to reject or drop the type of packet sent, which is ICMP. This is the lowest priority packet, so it's the most likely to get dropped when there starts to be congestion. So the second experiment was Twitter. So you can see again, this is the one with the average delay versus the router address. So we can see that the router address, with each hop, it increases. It increases linearly. It's not everyone, but I mean, it's generally speaking, it's an increasing scatter plot. So that's generally what we expect. The more hops, the higher delay. So that makes sense. And then this is the average loss per router address. So this is the loss percent in the Y and router address in the X by hop. And we can see that while there's not a super strong linear correlation, it does seem to be kind of like last time, that there's a it's very slight, but there's definitely a higher loss percentages in the later routers, right? Because these routers is 1, 0, 0, and 0.2, but these are like 0.2, 0.4, and 0.4. So that's definitely notable. And then we have the average delay versus time frame. So this is again where we take the average delay in the early morning amongst all routers in that trial, and we average them. And then we take it and we compare them by time frame, and we see that the early morning has the average highest delay per router, just like last time. Mid-afternoon has the lowest, pretty much just like last time, although mid-morning was right here as well. And then evening and night are later. But that is notable. So that is sort of a pattern we're starting to get there. So early morning and mid-afternoon. And then we get to average loss percent per time frame. There's no linearization or pattern, but we do see that mid-morning and mid-afternoon have the highest loss percentage per time frame. So then in the third experiment, there was no anomalies in Twitter, by the way. Twitter was pretty boring and easy. So Cambridge was the third experiment. And this one's interesting because we actually cross an ocean. So you can actually see that here. So this is the one with the routers in order of hops and average delay in milliseconds. So we see that it starts to increase like you'd expect, increased delay per hop basically. But then there's this huge jump. And so I did a little digging on the IP address locations and such. So this is actually an address in Chicago that then sends the packet to London. So everything here and onwards is a router in England. So what I believe is the case is causing this big jump is this this router in Chicago has large delays, like processing delays, propagating delays and stuff, and that's why this is so high. And then all of these have high propagation delays because they're crossing the Atlantic. So that's going to take a while. Yeah, okay. And this is the Cambridge average loss versus router address. So we see the router addresses here in order and the loss percent here. Again, there's no strong correlation, but you can tell that like there's definitely more, there's like higher dots here the farther we get into the trace. So like we see at the beginning, it's super low. This is also when we're in America. This is in America too though. And then we have all these higher dots in England. So it definitely seems like there is a correlation between average loss percent and the amount of hops, but it's slight. It's not that much. And then we look at average delay per router versus time frame. This is where we take the average delay per router for time frame, and we look at them and compare them. So we see that morning again has the highest average delay per router, and mid-afternoon again has the lowest average delay per router, with these three falling in the middle. This is obviously significant, and we'll see those compared momentarily. And this is the loss percentage. Again, this is notable because last time, if you remember, Twitter had the highest of mid-morning and mid-afternoon loss percentages, but now Cambridge has the lowest. So there seems to be a contradiction there. Maybe there's not a correlation. This is the anomalies. Trace route contained a double hop to the same IP address, and I only used one hop. This is a common trace route error, according to Google, it has to do with the time to live and such. So we just left it out. And then two routers experienced request timeout ping errors in the mid-afternoon and evening tests. These were also left out of the results, but it is important to note that mid-afternoon and evening, those are the same times that Seattle had errors in the middle of the trace. And I believe that there's a router or a set of routers or an area near me that gets very congested in the mid-afternoon and evening, and that this is what causes those packets those routers to drop the packets, basically. Makes a lot of sense, and that definitely, yeah, makes a lot of sense. So, and then there's also a large jump in delay time per router on the first graph that happens when the packet crosses in the Atlantic, as we talked about. All right, so then the big question, the million-dollar question, which frame has the highest delay? So we're comparing the average delay per router versus time frame by the experiment. So we see, basically the third graph that I did, average delay per router versus time frame, I took all three and put them on here. So we see that blue is Seattle, red is Twitter, yellow is Cambridge. So generally speaking, Cambridge had a higher delay, but we do see the pattern here. So in all of them, morning is the highest, and then afternoon is the lowest, with morning kind of making a case there in Seattle. And then these kind of flatten out a little bit, increase a little bit for mid-afternoon, but not significantly, and then night does its own thing. But that is significant. So we can pretty confidently say that time frame clearly influences the delay of internet traffic. Like you can see, like the delay is higher in the morning. It definitely is. There's no question. Okay. And then we look at which time frame has the highest loss percent. So this is less pretty graphs. This is so nice. Like look at that. And this has to do a little bit with the way the data is formatted in a percent form instead of raw numbers. However, you can see that there's no pattern here, right? So we got this one's going up and down, and this one's the reverse. It's ridiculous. All right. So loss percentage is clearly far more volatile than delay, and there's little to maybe even no correlation here between time frame and loss percent. However, we can see there's a little bit, like night does have a consistently high loss percent. It's the third highest here in Twitter, the second highest in Cambridge, and first highest in Seattle. So there is something there, but it's very slight, and there's no other like common data points. So we can't really confidently say that time frame affects loss percent. Okay, so overall, the time of day clearly influences the average delay of packets as they travel. The delay of packets is highest in the morning and lowest in the middle of the day. And that was the afternoon in this time frame. The loss percentage is much more volatile than delay of packets. While certain times of day sometimes have higher loss rates, this was the night that we just mentioned, this is not consistent enough to conclusively show that time of day significantly affects packet loss rates. And then we have the amount of hops and distance traveled so the amount of distance and hops that a packet travels clearly makes an impact on the average delay of each router. If there are more hops and distance, we can reasonably expect higher average delay. This was those linear graphs that were the first one in each experiment. And then the average loss percentage does not seem to be strongly correlated with distance or number of hops. However, we do tend to see higher losses at later points in trace. So they could be slightly correlated, but it is not strong in any way like it was with the average delay to number of hops. Thank you for your time, and have a great day.